Hello. In this project, we explored extensions to the dense fusion architecture as presented in Dense Fusion 60 Object Pose Estimation by Iterative Dense Fusion by Wang et al. We will be presenting our experiments for extending the dense fusion extraction from the 3D point clouds, the pixel-wise dense fusion, the 60 object pose estimation, and the iterative refinement.
For my part of the project, I investigated the semantic segmentation portion of the model. In the paper, the semantic segmentation takes as input an RGB image, although the overall model has access to a depth image as well. I propose using this depth image along with the RGB image for training the semantic segmentation. The overall model architecture is shown here. The red arrow points to the portion of the architecture that computes the semantic segmentation. Although the code made publicly available by the authors did not directly evaluate the per pixel prediction masks, it included a separate folder that computed semantic segmentation using an architecture labeled vanilla segmentation. This architecture consisted of an encoder-decoder structure that closely resembled the architecture referenced in the paper, but with additional decoding layers and batch normalization. The FuseNet architecture incorporates depth information as well as RGB information and consists of two encoding branches that share information, followed by one decoding branch that predicts the semantic segmentation of the given image pair. A comparison of the two architectures is shown here. The vanilla pose CNN only incorporates RGB information and consists of an encoder-decoder structure, while the FuseNet architecture consists of two parallel encoding branches and one decoding branch. The training plots for both models are shown here. Both plots show the loss versus number of epochs during training. The results of the semantic segmentation are shown here for both model architectures. For both metrics, the mean average precision and the mean intersection over union, higher is better. Both models perform similarly, but the FuseNet architecture slightly outperformed the vanilla model. This suggests that the overall model might improve with the incorporation of depth information for the semantic segmentation portion. However, due to the extremely slow training process, the performance of the overall model was not evaluated with the FuseNet architecture.
In this section, I will talk about my work on the proposed improvements to the iterative refinement and 6D pose estimation methods. The implementation of iterative refinement in dense fusion is the most time-consuming step. The author has recorded his best model at about 500 epochs, which on our hardware would take more than a month to train. In this project, it was proposed to use an LSTM in order to facilitate faster iterative refinement. We hope that being able to learn features in previous time steps would be able to help the model train quicker. The results of this experiment was a failure, as can be seen in the figure for the epochs versus validation distance here on the right. The model failed to learn. The accuracy was calculated using add and add-s for symmetric objects, as can be seen in this table on the left. I believe this failure was due to the fact that the data was temporally learned, but not in a typical fashion that is typically seen in models where data is given in where the time data is given in batches, whereas here it is given in epochs. In this paper, it is proposed to build a network that is capable of learning a network for both symmetric and non-symmetric objects. For our proposal, it was proposed by having two different networks, one learns symmetric and one learns non-symmetric objects, that both networks could learn their respective poses better. After implementing the code, training the model for weeks, and then reviewing the test results, I realized that I had an off-by-one indexing error where the non-symmetric model would learn the wrong objects. Nonetheless, on the bottom here is the loss for the non-symmetric-ish network, and on the top is the loss for the symmetric network. The results of the networks are seen in the last column, two columns here. The symmetric metric network performed as expected. However, the results of the non-symmetric network is nonsensical, likely due to the off-by-one indexing error.
My name is Jiaxuan Liu. In this 6D pose estimation project, I was responsible for improving the dense fusion network. In short, the dense fusion network fuses color and depth features on both pixel level and global level to suppress heavy occlusion and segmentation errors. The original architecture of the dense fusion network can be illustrated by this picture. This point fit 1 is the first set of fused features that focuses on the image information on the pixel level. However, besides the pixel level information, global information is also needed when estimating poses. Point fit 2 and APX are therefore generated to encode the global information. Point fit 2 is generated on top of the pixel level information, so it encodes the pixel-to-pixel relationship. APX is generated on top of point fit 2, so it encodes the global information of the image. The three sets of fused features are then concatenated together and passed into the post-estimation network. What I propose to improve the current dense fusion network is to add another set of fused features that is generated directly from the pixel level feature. This new global feature ideally will complement the original global feature because the original global feature is generated using the second level pixel-to-pixel information, which may be overly generalizing when being used to estimate the object pose. The figure suggests that the additional global feature helps my revised network achieve a faster convergence rate in terms of the testing loss. Thus will trigger the iterative refinement training in fewer epochs. The best models of the original network and the revised network were then evaluated on the line mode dataset, along with the pre-trained iterative refinement model. The evaluation results are shown in this table. Although the best model of the original network has a higher testing loss, when they were evaluated on the testing line mode dataset, it surprisingly outperforms our revised network. The reason for this discrepancy comes from the pre-trained iterative refinement model provided by the original research group. The iterative refiner uses the post-estimate of the dense fusion network as an input to correct its estimation error. However, the iterative refinement network is designed to work with original dense fusion network. If we want to see a better performance from our revised network, we also need to adaptively revise the post-refiner network so it can make use of the additional global feature. This is one thing we should try in the future, and this is also one of the limitations of our revised dense fusion network.